Welcome. So right now I'm going to talk about notation a little bit in the context of assignment 1, which I have just on the left here. So having a look at the first question, we've got two functions. We've got a function y, which sends the set of real numbers to the set of real numbers by y of x is 2x squared plus 3x all squared. So this part of it is not in the question. So looking at that question 1 there, we see a function y of x. It takes in input values x and it returns this, also a real number. Okay, so what I mean up here is I'm telling you what that domain is. It's the set of all real numbers. And this one here is called the codomain. It's not necessarily what comes out of the function, it's just tells you what comes out of the function is restricted to. So they cannot be a larger set than the real numbers. All right, now what is the real numbers? Well, you can think of that as numbers on the number line. Okay, so here we've got 0, and then here let's say we've got 1, here we've got 2, over here we've got -1. So far I'm just writing the positions of the integers or whole numbers. But between any two real numbers, there is another real number. So there's a real number here. Now that might be a fraction or a rational number. Okay, but between any two rational numbers, there's a real number as well. Rational numbers are the set of all fractions, where the numerator and denominator are integers and the denominator is non-zero. So this rational numbers. Okay, and then we have the complex numbers, which is a set that includes the real numbers. But anyway, so just some basics on sets and inputs of the function. So this says that the domain, the set of all acceptable inputs of the function, is just the real number. So every number that you can point out on that line is an acceptable input. So all possible real numbers. All right, now let's have a look at the second function. So we've got z of x equals x over the square root of x squared minus 1. Okay, now I have not given the domain here. So when I find the domain, I'm finding what's called the implied domain. So let's find what it is. All right, so you can see we've got a plot of this function in yellow or orange, however you call that. It looks a bit mustard to me. So there are no values between -1 and 1 at all, right? And the reason why is because when x is between -1 and 1, then the square is between 0 and 1. Okay, and so a number between 0 and 1 take away 1 gives a negative or 0. Both of those are not acceptable for the denominator here, because if the number is between 0 and 1, not including 1, then that denominator is negative inside the square root, which produces a complex number, not a real number. So looking at real valued functions here, we need that number inside the square root to be positive. Okay, now if x is equal to 1, then we have a 0 denominator, which is also not acceptable. And you can see what happens as we approach 1. We get values of positive infinite on this side and minus infinite on this side. So the domain for this function, or implied domain, is the set of all real x this says x is an element of the set of real numbers, and I put a colon for such that, so read that as such that x is strictly greater than 1, like what we see here, or x is strictly less than -1. Okay, continuing with the discussion of notation. So this is question 7 of the week 1 tutorial problem set. What we have here is a description of a two-variable function, f, from the set of pairs of real numbers. So that's the domain of the function. And the output is a real number. And it's given by f of x, y is the piecewise function xy squared over x squared plus y to the 4th if your point is not 0, 0. So I'm running out of space here. So let's see if I can fit it in. If x comma y not 0, 0. And then we say that it's 0 otherwise. Okay, so this is the description of our function. Now what we have here is the domain. This set on the left after the f is always the domain. So I'm just telling you that that is the domain there, being pairs of real numbers. Now remember, if I want to write this in set notation, 2 space is the set of all pairs x comma y such that both x and y are real numbers. Okay, now remember what this says is an element of. X and y are elements of the set of real numbers. They're real. So here I mean such that, here I mean that this is just what f does. Okay? So my inputs are pairs of real numbers or points. And out comes a real number, and this is explicitly what that rule says to do. Okay, so let's consider a geometric picture of this. Now, this problem is a lot like one of your assignment questions if you're doing this in 2024. And that was on showing that a surface had a discontinuity at a particular point. In this case, the point of interest is the point 0, 0, or the origin. So we want to show that along 2 different paths, we don't end up at the same place. Okay, and so here I've given 2 examples of paths where this happens, but if you wanted to try this yourself without this hint, you could take any 2 paths that contain the point 0, 0 that pass through it, right? So for example, y equals 0 contains the point because 0, 0 is on that line. Okay, so y squared equals x also contains the point 0, 0 because 0, 0 satisfies that equation. So both of those 2 paths contain 0, 0, but they're not the only 2 paths you could have shown or used to demonstrate that this function is not continuous at 0, 0, and hence not continuous. And it so happens that sometimes for some multivariate function, you take several paths and you end up getting the same limit as the point xy goes to 0, 0, for example, or AB. And so one of 2 things would happen. Either the function is continuous at the point of interest, or it's not, and you just haven't found yet a path that demonstrates that it's not continuous. All right, so here I've got some geometric pictures. So this one here, I'll move it around a little bit, but you can see a picture of this surface here, xy squared over x squared plus y to the 4th. Now, if you peek in here, you can see something strange going on near the origin. So I have shown the 2 paths here. The red one is the path y equals 0. And so you can see if you follow it, it does take you to the point where x is 0 and y is 0, the origin right here. Okay, likewise, here we have this green parabola. Now notice it sits on the surface. So along the path, y squared equals x, or x equals y squared, that also goes towards 0, 0, but you can see that they take you to two different heights. Okay, so we're going to learn that the limit as xy goes to 0 along these two different paths take us on the red path to 0 and on the green path to 1/2. And since those two are not equal, this function is not continuous at the point 0, 0. Okay, now let's just note one other thing. If we take this way, we can peek through there, right? However, and it looks like this green little tube is not fully on that surface, but it actually is. And so the fact that we can see some daylight through there is just probably that we didn't plot enough points in the rendering of this graphic, right? So the computer's having a hard time rendering the graphic near the point 0, 0 because there's a whole lot of extreme values. All right, so now let's look at this from above. So if we look at this from above, we have more of a two-dimensional picture. I'm trying. Okay, hang on. There we go. Something like this, looking at it from above. So this is what you would get if you plotted those two paths in the xy plane. So if I scroll down, you see here they are. I've just plotted those two paths in the xy plane going to 0, 0. All right, so now, and I know that most of you would have done this in the tutorial, but for the sake of it, I'm going to do it again because that tutorial's already happened. So you might get something out of this. Okay, so how do we show this on paper? Well, what I want to do is take the limit as the point x comma y goes to 0, 0 along the first path C1. And remember that C1 is just the path y equals 0. So how do we take this limit? Well, I take this description, and everywhere that I have a y, I replace it with a 0. So that's x times 0 squared, and we have x squared plus 0 to the 4th. But I have a function of x, so I'm interpreting this now as a limit as x goes to 0, because there are no y's in it, right? So xy going to 0, 0, and this is x going to 0. So I have a standard one variable limit now. Now the numerator is equal to 0. The denominator is x squared, so this entire thing is 0 before we even consider the limit. So we have the limit as x goes to 0 of 0. Now remember, we're not evaluating this at 0. We're just taking the limit, meaning taking x going extremely close to 0, but not equal to 0. Looking at what that is. Okay, so along this path, the blue path here, that takes us, as we get extremely close to x equals 0 along that path, the height there is 0, right? Just like what the function tells us the value is at 0. So we go back to this, let's have a look along that red path. We have 0, extremely close to 0. Now let's do the green path. Okay, but we haven't taken the limit yet, so we get 0. All right, now we'll do the green path. So the limit as the point xy goes to 0, 0 along C2, I just put that over the arrow. Okay, we're taking the limit of f of xy. And so now what we're going to do, because C2 is the curve or path, y squared is x, so I can do everywhere I see an x, I can replace it with a y squared. So we have y squared times y squared over y squared squared plus y to the fourth. And now, since I have y's everywhere, I can consider this limit as a limit as y goes to 0. Okay, so now we have the limit as y goes to 0. Simplifying this, that's y to the fourth over y to the fourth plus y to the fourth, which is 2y to the fourth. Now I can cancel this because it's a limit. I'm not evaluating this at y equals 0. I'm just evaluating this extremely close to y equals 0. So I have the limit as y goes to 0 of 1 over 2 because we can cancel the y to the fourth there. Okay, now this limit is a half. And notice that 1/2 is not the same as 0. So we have two different limits. And so then we can conclude that since we have two different limits along two different paths, that the limit as xy goes to 0, 0 of f of x comma y does not exist because it's ambiguous. And hence, if it doesn't exist, cannot be equal to the value at the function. I mean, the value of the function at 0, 0 cannot be equal to this, right? You know, incidentally, this was set out to be equal to 0, but it can't be equal to this because this doesn't even exist. So therefore, it's not continuous at the point 0, 0. So we'll say, so f is not continuous at 0, 0, and hence the function is not continuous on the domain. Hence, nor on the domain set of real numbers superscript 2. Run out of space here, but I hope that's okay. All right, so this hopefully should give you something to think about with your assignment because it's set out in a very similar way. All right, so now I want to go back up and have a look at the one variable function f of x equals x squared plus 3x plus 1 if x is greater or equal to 1, and 1 minus x is if x is negative. So let me just go ahead and plot this for you. All right, so to do that, I need to put in a conditional or an if. And let's get some clean paper, turn that over. So I'll just write in an if here. So if x is greater or equal to 0, then I want x squared plus 3x plus 1, and then otherwise I want 1 minus x. All right, so that is a conditional giving me this definition there. But incidentally, the domain of this function is all real numbers. All right, so now I just want to plot that in some region and then talk about it. Okay, so here we have this function. Now notice the scale on the x-axis is not quite the scale on the y-axis. So the way you sketch this might be somewhat different. So I mean, I can fix this up, right, by saying something like aspect ratio 1, 1, and then plot range, chopping it off. Let's chop it off at, say, 5. Okay, so this is possibly a more realistic view of this. I'll scoot this down a little bit more. All right, so I want you to notice a couple things here when we plot this function. So on the left, we've got just a line, right? And then on the right-hand side of 0, we have a quadratic function. There's a little bit of a curve in it. Now ask yourself, can you draw this function without lifting your pen up? The answer is yes, right? You can indeed do that. So intuitively then, you know that this function is continuous at this point where things change. It's continuous at 0, and because each of these things are polynomials, they're continuous otherwise. So this function, f of x, is continuous on the whole real number line. However, it's not differentiable, right? You notice there's a sharp point when x is equal to 0. When you have a sharp point at a particular point, well, then it's not differentiable at the point, okay? But what I can also do is I can plot the first derivative. So let's do that. We'll plot the first derivative. So what I need to do here to do that is just replace this with the first derivative there. So that would be 2x plus 3. And then the derivative of 1 minus x is just minus 1. Okay, let's press the button. And then I need to change the plot range. Let's go minus 2 to 5. Okay, here we go. So here I have a plot of the first derivative. The x-axis is there, and then what we have on the y-axis or the vertical axis is f dash of x. So you'll notice that I cannot draw this function without lifting up my pen to continue up to the rest of it. So this function, the first derivative is not continuous. Hence, since the first derivative is not continuous at 0, the original function is not differentiable at 0. Alright, so I'm pretty sure that there's a theorem that says if a function f of x is differentiable at a point, then it's continuous at the point. But let's just Wikipedia this. Differentiable implies continuous. If a function is differentiable, then it's also continuous. The property is very useful when working with functions, because if we know that a function is differentiable, then we immediately know it's continuous. But the other way around doesn't work, as the example I just showed you suggests, right? If a function is continuous, it doesn't necessarily mean that it's differentiable there. All right, so back to it. Why am I showing you these things? Well, because in multivariate calculus, this sort of thing forms the conditions of a great number of theorems or results, right? And so there's a result called Clairaut's theorem that says the partial derivative, or second partial derivative, f subscript x comma y, is the same as f subscript y comma x, provided a condition like these, right? Provided the derivatives exist and they're continuous. Okay, next I want to talk about two really important functions in mathematics and science and engineering and physics and so on. Okay, so they are cosh of x and sine of x. Okay, how are they defined? Well, cosh of x is 1/2 e to the power of x plus e to the minus x. So you see, it's not really all that exotic. It's just sums of powers of e. Remember, e is 2.718281828 and so on. Let's just find out exactly what it is. exp of 1.0. Okay, so there's e, 2.718281828. 459,045, and so on. So what you know about e is that it's the base of the natural logarithm, and e to the power of x has a derivative which is the same function. The derivative of e to the power of x is e to the power of x. Okay, so you see then that this is not too far beyond what you already know. Now, sine is defined really similarly. E to the x minus e to the minus x. Okay, so cosh and sine. All right, so one thing to notice here. Now, you see the naming of these this looks a little bit like cos and this looks a little bit like sine, doesn't it? That's not a coincidence, because there are really close relationships between sine and cos, and I'm going to show you some of these. So the derivative d on dx of sine of x is cos of x. Okay, let's take the derivative of sine of x. D on dx of sine of x is the derivative of 1/2 e to the x minus e to the minus x. Now, treating this as a differential operator, which it is, we can allow this 1/2 to float through it and apply it to each one of these things. So we have 1/2 derivative of e to the x minus the derivative of e to the minus x. Now, the derivative of e to the x is e to the x. The derivative of e to the minus x, well, that requires a chain rule, but the derivative of the derivative of minus x with respect to x is -1. So that -1 comes down, goes together with this -1 and makes a plus. So what we have then is 1/2 e to the x plus e to the minus x. And so we notice, yeah, that's defined as cosh. Okay, so just as the derivative of sine is cos, the derivative of sine is cosh. Now the derivative of cos is minus sine. Okay, the derivative of cosh is sine. And you can check this, right? Just like what I did here, you can check that. Okay, so does the analogy stop there? No, it doesn't. It keeps going. So let's think of some other similarities between sine and cos and cosh and sine. Okay, so I'll grab a new piece of paper. All right, so let's talk about parameterization of the circle. And by the circle, I mean the unit circle, the circle of radius 1. All right, so if I just draw a point on it, come down, this distance from here to here, let's call that x. And then this distance from here to here, the origin to this point, is the radius, which is equal to 1. Now the height, let's call that y. Okay, so that would make this the point x comma y on the circle, and we know it satisfies x squared plus y squared equals 1. All right, so let's put an angle t in here, the angle across here. So can we represent x and y in terms of cos and sine of that angle t? Well, yes, we can. So let's have a look at cos of t. Cos of t is adjacent on hypotenuse, right? So that's x over 1, which is x. And sine of t is opposite on hypotenuse, so that's y over 1, which is y. Okay, so what we have then is x is cos and y is sine. So this here is cos of t, sine of t. And in fact, if I come on the computer here and I ask for a plot of the points, cos of t, sine of t, right? There I've written the point. So I'll write now parametric plot. As t goes from 0 to 2 pi, because this is done in radians, that's the full circle. Let's have a look. You see, I get the full circle. So I have essentially parameterized the unit circle by calling the points cos, comma, sine. Okay, and this works because of this, but we also get from that cos squared t plus sine squared t equals 1. Okay, so how do you get the sine wave out of this? Well, if you just look at the height as you go around here, well, the height is exactly a wave, right? It's the sine wave. And the same thing for the position on the x-axis. That is a cosine wave as you go around. So we start at 1, then it starts decreasing, and so on. Now I could animate this for you, but my main focus here is on cosh and shine. Okay, so is there an analogy between cosh and shine of what we have here, this parameterization of the unit circle? Yes, there is. All right, so what we're going to do is square cosh and square shine. So cosh of x, remember it was 1/2 e to the x plus e to the minus x. Okay, so let's square it. So cosh squared of x is, so 1/2 squared is 1/4. And then when we square e to the x, we have e to the 2x. And then we multiply these two together when we square this and then double it. So we'll have 2 e to the x, e to the minus x. And then e to the minus x squared is e to the minus 2x. But we can simplify this a little bit because the product of these two, since we can add the exponents and get a 0 exponent there, product of these two is just 1. So we have a lonely 2 there. Okay, so we get 1/4 e to the 2x plus 2 plus e to the minus 2x. Now let's do the same thing for shine. So shine of x is equal to 1/2 e to the x minus e to the minus x. So squaring that, shine squared x is 1/4 e to the 2x minus e to the x, minus 2 times e to the x, e to the minus x, plus e to the minus 2x. Okay, and simplifying that, similar to what we had above, we have 1/4 e to the 2x minus 2 plus e to the minus 2x. Okay, so now these two lines here are indeed really similar, aren't they? The only difference is the sign of that middle term. So let's see, if we take this line minus this line, everything will vanish except for 2 minus minus 2 all over 4, which is 1. So taking a difference, we see that cosh squared x minus shine squared x is equal to 2 minus minus 2 all over 4, which is 4 over 4, which is 1. Okay, so now if we let uppercase x be cosh of lowercase x and uppercase y be equal to shine of lowercase x, then what we see is that uppercase x squared minus uppercase y squared equals 1. Right, so that is a hyperbola. So we have a parameterization of the hyperbola. So let's just take this little piece of code and change it slightly. Put a h there and a h there, and so now we are parameterizing cosh, comma shine. We should get a hyperbola. Okay, so let's have a look. Now I didn't get the whole thing. It more or less looks like a straight line at this point because I need to take this over a bigger set of t values. So say from minus 2 pi to 2 pi. Okay, so now you see at least one branch of a hyperbola, but let's draw an entire hyperbola here. Okay, so here we have a hyperbola, right? So what we've got here is just the right-hand branch of it. And the reason why this one looks more like two lines is because it goes down to minus 100 and up to 100, right? Whereas this is only plotted from minus 3 to 3. So there, you see a lot more of the curvature in this plot. Okay, are there other analogies between these? Well, there are, provided you're willing to consider complex numbers. Okay, so let's briefly talk about complex numbers. So, complex numbers, and this by far won't be a complete discussion. So we have the number I, which we call the square root of minus 1. Okay, but there's this nice property relating I to e and pi, and so that is e to the I theta is cos theta plus I sine theta. And I'm pretty sure this result is due to Leonard Euler. Okay, so that if you take theta equal to, let's see, what do we want? We want this one to be 0, this one to be minus 1, so that would be pi. Okay, so e to the I pi is cos of pi plus I sine of pi radians, and in this course it'll always be radians rather than degrees because of this nice identity in others. So sine of pi is 0, cos of pi is minus 1, so this is minus 1. All right, now this is said to be the most beautiful relationship in mathematics, so if you think it's beautiful, then it's beautiful. I think it's kind of nice. All right. So now that we've had a really brief talk about complex numbers, what's the relationship between cos and cosh? Well, cosh of x is equal to cos of ix. And just to make sure I've got that right from memory, because it is from memory, let's just try cos of 1.0 I. Okay, so we get 1.54308 and so on. So now below that, let's try cosh of 1.0. Okay, we also get 1.54308, but we don't have the imaginary part. Here, you see we've got an imaginary part of 0. That's the part with the I next to it. Okay, and if I press the button after that, yep, it's still 0, right? We've got more decimal places on this one, but this one is still 0. So these two things are the same, right? And in general, they are the same, because if I change this to, say, 3, I'll get the same number again. Okay, so we have an identity here. Now, there is a similar identity for shine. And I think it's minus I sine of I times x. But let's try this. I'll change this to sine, and then there should be a minus I in front of it. And then this should be shine. Okay, yes, we get the same number. So we have these two identities here. All right, so another thing, and I probably did this in a video somewhere earlier, is what is the use of this? Well, cosh and shine, and I'm reaching into very vague memories here, but the way an electric cable or telephone cable wire hangs, I think it's modeled by one of these. All right, but also they're useful in mathematics and engineering and so on, because if we're looking at, say, this integral, let's make sure I get the right integral here when I describe it. So just type in an integral and I'll have a look at the answer. Is it x squared minus 1? Not sure yet. So no, maybe it's plus 1. Yeah, so I want a plus in here. Okay, so the integral of 1 over the square root of x squared plus 1. All right, so Mathematica is telling me that the answer is arcshine, or the inverse shine function of x. So that's telling me that I should make a trig substitution. I say trig substitution because I loosely think of these as trigonometric functions, even though they're hyperbolic functions. So I'm going to say let x be equal to shine of, say, t. Okay, and so next what I want to do is differentiate. So dx on dt, well, we know what the derivative of shine is. It's cosh. So that's cosh of t. And so this tells me how I want to substitute that dx in terms of dt's. So far we have the integral of 1 over the square root of shine squared plus 1 shine squared t plus 1 dx. But here I'll think of this temporarily as if this were a fraction, so that I can algebraically solve for dx, so that I then know how to replace dx. Okay, so this, if I do that, then I get dx is cosh t dt, right? But I don't say that, I just say replace dx with cosh t dt. So that here, let's do that. So we have cosh t dt. And then in here, some more magic happens, because remember how cosh squared minus shine squared equals 1? So that tells you then, if you take the shine squared over to the right-hand side of that equation I just spoke, then cosh squared is equal to shine squared plus 1. So what we have then inside this square root is cosh squared, and so this thing is 1 over cosh. So the integral is 1 over cosh t cosh t dt. So we can cancel these, and that's the integral of 1 dt, which is t plus c. Okay, we're not quite done, but hey, it's really simple, isn't it? So to express this in terms of x, we need the inverse function of the shine function, because we have x equals shine of t. So applying the inverse function to both sides, we have t is arc shine, or the inverse function of the shine function. So arc shine of x plus c, exactly like what Mathematica gave me here. Okay, but this brings me to discuss inverse functions with you really briefly. So I'll scroll up to where I talked about this earlier with someone else. Okay, so what I've done here is I've plotted shine of x, I've plotted y equals x, and I've plotted the inverse function arc shine of x. So the blue one is shine of x. So you can see that when x is positive, it acts more like e to the x, or in this case 1/2 e to the x. And that's because e to the minus x for large positive x, that becomes trivial in size, right? So this is dominated by e to the positive x. And so away from 0, this is 1/2 e to the x essentially. And then on the other side, well, the term with the minus in it, so 1/2 e to the minus x dominates, because if you're inputting minus values, then you have a positive exponent in that term. And so that comes down here, just like the other side. Okay, so now I've got the line y equals x there, Because if I take a mirror image of the line, of the curve y equals sine of x, mirrored about the line y equals x, I will get this green curve. And that is the inverse function arc sine of x. So you can think of an inverse function as a mirror image about the line y equals x. Now, inverse functions do not always exist. They exist for the domain such that your original function is what we call one-to-one. And it does so in what's shown here. So the inverse function does exist for those x values shown, right? And so that's arc sine here. So you can see arc sine, or the inverse function, is not that exotic a function either, okay? And that's how this integral is given in terms of arc sine.